So thank you for the introduction, Blair, and thank you for joining everybody. I'm going to talk to you today about 3 use cases from 2 application areas, namely optimal fiber networks and optimal shop footprints. After that, I will turn to what we call the graph ILP API. So that's our try to create an API for creating ILPs from graphs. Now, I hate abbreviations and acronyms, so I'll spare you any but those 2. Guess everybody knows what an API is, and ILP, of course, stands for integer linear program or integer linear programming. Knowing that this is a Gurobi webinar, assume that everybody has a basic idea what an ILP is. But if you don't, there will be 2 very simple examples for ILPs, 2 slides ahead. So I think they should give the basic idea of what ILPs are about. Now, I represent a team of roughly 20 data scientists in the consumer business unit of Vodafone Germany. And as data scientists, we tend to be programming in Python. So for this reason, we are also using Gurobi's Python API, and we're also basing our own API on top of the Gurobi Python API, and of course, we'll also be in Python. Let's look into those use cases. The first one is about optimal fiber networks. So the question of how to connect customers to our fiber network with an optimal return on invest. So laying fiber, of course, has a certain cost based on the construction work that is needed. I want to find fiber networks that are as short as possible in order to have the building cost as low as possible, but connect as many potential customers as possible. Before I start with the use cases, let's look at some of the graphs that are lurking in the background, not in Great Brexit as the map is indicating, but behind our problems. So often we can model our problems as graph problems. So in our first use case, fiber optimization, we have a graph as indicated in the red box. So we see a road map of a town in Germany, and we have on the one hand road sections as the edges in our graph, purplish in this map, and they are connecting certain vertices in the graph, which are either road crossings or potential customers, so the red dots in the map, or the green dots in the map, sorry, and possible access points to our existing fiber network, which are the red dots in the map. In the second set of use cases, which you can see in the map on the right, we have a different graph where the vertices are given by the shops that we have in Germany, both own shops and franchises. A pair of shops is connected if there is some influence of one shop on the other, assuming that you close one. And the type of influence is about whether people who tend to buy in one shop would move into the other, taking that the first one where they actually want to go is closed, rather than moving off to other channels like online or telemarketing or to the competition or staying away. Okay, but more about that later. So the important thing here is we have graphs underlying both of our problem sets, and thus there's a certain joint structure here. The first question is how to go from a graph or a problem, say an optimization problem on a graph, to an integer linear program. And here is a rough template of how we tend to do this and how it's usually done. I've indicated a graph in the upper left with vertices represented by little balls and edges between the vertices by these blue and red magnets. And as usual, a graph is a pair VE with V a set of vertices and E a set of connections between vertices called edges. So usually our solutions give us a subset of the graph. So either a subset of the vertices that are part of the solution or a subset of the edges or both. So we introduce binary variables for the vertices and edges. So if we have an edge U, we introduce for that a binary variable XU, indicating of whether that vertex is part of the solution or not. And similarly with an edge WUV, here we introduce a variable XUV, indicating of whether that edge is part of the solution or not. Our edges are often weighted. This is indicated here by the weight WUV. And for example, in our first set of use cases, fiber extension, that weight might indicate how expensive it is to build fiber along a certain road section, which is represented by the edge. In the second part, it might indicate how much of the sales volume of one shop would flow to the other shop if the first one is closed. Also, the 7 in a little yellow box here indicates that we often put labels on vertices, and that's sometimes an auxiliary trick that we can use to formulate our integer linear programs. So with these variables at hand, we can formulate integer linear programs that will solve our problems. And let's look at 2 very simple and ubiquitous examples that can illuminate how this works. So the first one is example 1, maximum weight matching, where indeed we have a weight on each edge in the graph, and we try to maximize a linear objective, namely the sum of the weights of the edges which are part of the solution. But there is an additional condition. You can't just choose any edges, but you need to choose them in the way that each vertex is adjacent to at most one edge. So again, we maximize this sum that we see in the lower left of the product of the weight of each x times the indicator of whether that edge is chosen, subject to the constraint that only or at most one edge adjacent to each node can be chosen. That's the last equation on the lower left. A similar problem is the minimum vertex cover problem, where we are trying to select a set of vertices in the graph such that each edge is adjacent to one of the vertices that is selected. So again, this is an optimization problem on a linear objective, this time a minimization problem. We want to minimize the number of vertices chosen such that all the edges are covered. So in this case, we're just minimizing the sum over the indicators of all the vertices. So that's just counting the number of vertices in the solution. And then the constraint here is given such that each edge should be adjacent to one of the vertices that are chosen for the solution. And you can see all the constraints are also always linear, and ILP, we can have linear equations or inequalities. So the previous problems were comparatively simple in the sense that there was little structure in the solution sets. So especially in the second one, vertex cover, any subset of the vertex set can in principle be a solution. Now we come to a problem that has a bit more structure in the solutions and is that somewhat harder to express as an integer linear program. But let's start with the problem, which is to find the shortest network connecting potential customers in an area. So we're seeing the road network of a suburb of Munich here, and it's a graph as described in the beginning, right? So we have the road map network comprising the edges of the graph and road crossings plus the potential customers connected to the road network as the edges, as the vertices. And what we want to find is, again, the shortest network connecting all these potential customers, i.e. all the red dots here. And already with a problem this size, it's utterly hard to do that by hand. I guess you wouldn't find a solution by hand here. And it's also hard for computers from a certain instance size because this is an NP-hard problem. As long as we are in the range of realistic problems, so I don't know, the size of a suburb or city graphs with a couple thousand vertices, say, this can still be solved by computers. And that's especially the case if you have a fast ILP solver like Gurobi in the background. And that's one of the reasons why we chose Gurobi to solve this problem. Here's a solution for the problem that comes out of the optimizer. And it's not just one such solution that we're looking for, but one of the fields of application that we are using it for is for extending our fiber networks in so-called business parks. These are areas designated for offices or businesses to settle, and got around 32,000 such areas in Germany. This means we don't just want to solve one of those problems, but rather 32,000 of those problems. And as usual, business wants their answers quickly, not in a year, but next week. So you have to solve all those instances rather. Underlying graph theoretical problem connecting a subset of vertices with a network that is as short as possible is known as the Steiner tree problem in graphs. And this can be cast in several ways as an integer linear program. And we will look at 3 ways here to do this. And as I mentioned a moment ago, this is now a bit harder because of this additional constraint that we have, that the answer needs to be connected, because a disconnected fiber network, of course, doesn't work. We somehow need to find the constraints describing the fact that the solution, so the subset of edges that comprise the connecting fiber network, is actually itself connected. We have a small number of definitions before we can describe this. So first of all, again, we have a problem on a graph G, which has a vertex set V and an edge set E. And we're looking at weighted undirected graphs here. Also, the size of the vertex set is abbreviated as N. And in the vertex set, we have a subset T of so-called terminals, which correspond to the red dots in the example on the last slide. So those are, in our case, the potential customers to be connected. Now, in order to be able to describe the fact that the solution should be connected, we use a definition which is called a cut in the graph, which you can define for any subset of the vertex set. And it's essentially the set of those edges of the graph which connect a vertex in the subset that's defined in the graph to a vertex in the complement of that subset. So in the graph, but not in that subset. And now we can go on and then first do something very similar to the previous slide. So we have a minimization problem here. So we are in the left-hand box on the slide. We want to minimize the building cost for the fiber network, which corresponds to the sum of the edge weights corresponding to those edges which are part of the solution. So that's again the weighted sum that we see in the first row here. So edge weight times edge indicator, so that only those weights are counted that are part of the solution. And that's, of course, something we want to minimize. Then we have our constraints describing what our solution actually should look like. Otherwise, you just would choose the empty solution and find a minimum. First of all determinants should be connected. So we have an indicator variable for each vertex saying whether it's connected by the selected edges or not. And those corresponding to the terminals should, of course, be 1, i.e. the terminals should be connected to the network. Then there should be a relationship between the edge and the vertex variables, telling you that you can only choose a vertex as part of the solution if there is an edge connecting that vertex to the solution. And those are the next 2 constraints. And the final constraint is the tough one, the one that is actually making sure that your solution is connected. And it essentially says that whenever you have a cut in the graph, so putting your vertex set into a subset and its complement, then if there are terminals in the subset and in the complement, then there should be an edge bridging the gap between those 2 subsets of the vertex set. The last equation on the lower left. And it's actually not one equation, that's the painful bit here. It's even an exponential number of equations, because the number of subsets of the vertex set is, of course, exponential in the number of vertices. This is a problem because with, say, 1,000 vertices, an exponential number of vertices, exponential in 1,000, is very, very large, and you can't actually even describe all the constraints to the solver at one time. So the good thing about Gurobi is that it has this callback concept. So you can actually add constraints to the optimization procedure while it's running. And then a typical strategy is to only add some of those constraints, find an incumbent solution, and then check whether it's connected, for example, by shortest path techniques. And then if it's not connected, you find out which constraint for which cut is actually violated, and then you can dynamically add in that constraint and find the next incumbent until you find an incumbent that is actually connected. and then you know you've got an optimal solution. So an alternative to that is to find a smaller constraint system, and then that's given in the middle box. It's a linear size constraint system in the number of edges, and this means that you can give the whole constraint system to the solver from the beginning, which makes the use of the solver's heuristics a lot more effective, and also you get an accurate lower bound from the solver from the beginning, which is not possible in the left-hand case because the solver doesn't know all the constraints. So let's look at how this formulation works. So we've got the same objective. We're still trying to minimize the sum of the weight of the edges that are part of the solution. We still want all the terminals to be connected. We still want that you can only select vertices when there is an edge adjacent to the vertex that is also part of the solution. And now there is this linear equality constraint that I've marked with a little arrow, which is the trick here. It is telling you that in your solution, the number of vertices should be one larger than the number of edges in the solution. And this enforces solution is connected. It's a tree, which is great because optimal connected solutions to the Steiner tree problem, and that's why it's called Steiner tree problem, are trees. Whenever you have a circle, you can simply delete one edge, have a connected solution, and one that is of lower cost. And if you do not have a connected solution, this enforces a circle in your solution. And now all you have to do is forbid circles. And that's what the last two equations here do, or inequalities do. It's a labeling trick. So we are actually working with directed edges here. And we make sure that if you go along a directed edge of the solution, then the vertices adjacent to that edge have labels, which are integers, and they need to increase from one vertex to the next if you go along a directed edge. And then if you think about a circle in the graph, it sometimes comes back to a previous vertex, and this already has a label, and along the circle this was increasing, so now it can't increase anymore. You have to hit a smaller label. So this is actually making sure you don't have circles in your solution. So this is nice because even though it looks more complex, if you look at the number of equations in the text, the actual number of constraints is smaller. It's just linear in the number of edges, which in the worst case is quadratic in the number of vertices rather than exponential in the number of vertices. The problem is that this probably has a worse integrality gap than the left-hand side solution. So good side is you can tell the optimizer all the constraints from the beginning. You always have a correct lower bound on the value of the solution, and heuristics do the right thing from the beginning. However, it's not as tight to the solution as the exponential size constraint system. So that's why we were looking for a trade-off between these two, which is described in the right-hand box. This is telling you, okay, let's start with the linear size constraint system, but try to make it tighter by adding more constraints, but fewer than all those exponentially many. And one way to do that is to add, for example, some of the circles and forbid them explicitly in the constraint system. And a nice set of circles is, for example, a set of circles comprising a so-called circle basis. So a set of circles from which all the other circles in the graph can be constructed. Also, trees and graphs have the nice property that they are two-colorable. So that's another set of constraints you could add, adding additional labels, producing a coloring of those vertices which are part of the solution, and put a constraint that should be a two-coloring. So you should be able to color the solution with two colors such that any two adjacent vertices get a different color. And then this indeed converges somewhat faster than the pure linear size constraint system. So you have a bit of a trade-off here. Yeah, I've also put a question on the slide to ponder for perhaps if somebody from the Gurobi team is here, or if somebody is thinking about actually writing ILP solvers. whether it's not possible to run several such formulations in parallel and make sure that the solvers exchange information about upper and lower bounds and perhaps incumbents while they are running, and thus have something that is the best of all worlds. So that's how to cast the Steiner tree problem as a integer linear program. And that's kind of the quick introduction to our problem of finding optimal fiber networks. Now, the next application area is the optimization of our shop footprint, and also related to our shop footprints in a moment, the question of how to reopen shops after the COVID lockdown. So finding a way to open as few shops as possible, but also serving as many customers as possible at the same time. So let's start with generally finding an optimal shop footprint under certain conditions, like trying to keep the footprint small but maximize contribution margin or revenue, or minimizing cost but keeping a certain amount of inflow. All those types of scenarios we would like to be able to play through with optimization scenarios. And this is a combination of both machine learning and integer linear programming. So on the one hand, there is a step where we want to be able to predict what is happening if we close or open a shop, just a single one at first. And we're training machine learning models to do so. That's the first step. And these models, again, are predicting the sales volume of a shop that is opened, or how the sales volume of shops close to one that is closed actually change. So this is kind of the things you can play with in the optimization. You can close some shops, you can open other shops, and you, by combining those two things, find an optimal footprint under certain conditions. Now, the machine learning models do something non-linear here. So they are also good at predicting what's happening if you close two shops in an area, which is probably not linear. So it's a different thing to close either shop A or shop B in the same city, and add those effects, or to actually close both shops. So that's expected to be non-linear, and that's something that the machine learning models can cover pretty well. However, you can't play through the whole combinatorics of that, right? You can't go through all the possible subsets of our roughly 1,500 shops and look at what's happening if I close them. Not even if you look at a realistic number of shops. Of course, you're not going to close 90% of your shops, but still in realistic ranges, it's too much of combinatorics. So a first integer linear programming thing that we're doing is trying to break down our shop graph into manageable clusters. Again, our shop graph consists of shops as the vertices, and an edge between two shops indicates that if you close one of the shops, there is an influence on the sales numbers of the other shop. So typically, if you close a shop close by to another one, the sales figures of the other one should rise because customers are moving from one shop to the other one. And these are again weighted edges, so the weights at the edges tell us just how much the volume of the other shop changes if we close the first one. So what we want to do is chop this graph down into small connected components on which we can play through all the combinatorics of closing shops in a way that when we want to do that, we are actually cutting edges in the graph, and we want to cut a total minimal weight of such edges. So we want to lose as little information about the influence between shops as possible. And this is something we actually formulate as an integer linear program, and this gives us smaller clusters. And finally, if we run through the combinatorics of those clusters with our machine learning models, then we can set up a larger integer linear program. This is step 3, to actually find a countrywide optimal footprint. So let's look at this in a bit more detail. On the left-hand side, again, we have the full shop footprint graph, and again, we do a first ILP doing the clustering on it for us, creating small subsets of the graph that interact with the shops outside of it as little as possible. And now we can look at the combinatorics. So this is in the bottom middle of this slide, where you see several combinations of closing one shop, closing two shops, closing three shops, and you can actually play through the whole combinatorics of that and see what the machine learning models predict for each so-called state of a cluster. And now this gives you pairings of clusters and their value. So the more shops you close, probably the more the value of the cluster reduces, but also the cost of the cluster reduces. So these are information that you can put into a countrywide footprint optimization ILP. So that's one set of information. And a nice thing about the Gurobi API is that you can actually model this mapping from different scenarios in one cluster to its value by piecewise linear constraints. On the other hand, of course, each such local closing scenario induces the information of which shop is closed. So you can introduce for each shop a variable indicating whether it's open or closed in an incumbent solution. You can multiply that by any attribute that you have per shop. So things like per shop cost, per shop revenue, per shop contribution margin, whatever. So on the one hand, you can make the ILP play through the different closing scenarios in each cluster, giving you the results from the machine learning models for each of those scenarios that you can put into your ILP. And on the other hand, you can put per shop information, and then you can combine those two things to formulate your constraints and also your objective for the ILP. So here's a template example of what it could look like. So here again, if you have a value per cluster, say the revenue that you retain in the cluster when you close some shops, you can multiply that by kind of the indicator for the cluster, and it's going to tell you if you choose a certain combination in that cluster, what its value will be. And you want to maximize that value, which without constraints would mean you just leave all your shops open and also open as many additional shops as possible. But perhaps you have additional constraints, like you only want to keep a 1 minus epsilon fraction of your total current number of shops open to optimize your footprint. So I don't know, you want to go down to something like 95% of your shops, but still retain as much value from the shops as possible. And you can, that's the nice thing about it, play through many different scenarios here where you can both optimize for different aspects, revenue, contribution margin, cost for different products, and so on, and put any type of constraints that you can think of on it. So like keeping a certain fraction of sales in a certain type of product, for example. So this is the first use case that we have in the application area of our shop footprint. The second one is the reopening of shops after the COVID lockdown. So here on the left-hand side, you see again our shop footprint. And in the lockdown for a while, all those shops were closed. And at some point, the question was, if we can open just some of those shops, what would be a minimal such footprint? So opening as few as possible, but making sure that every customer has a shop near to him. And on the left-hand side, what you can see is some shops are selected as the red circles, which are some shops that business said they must be open. They must be part of the solution. It's also a nice thing about using interlinear program. It's easy to formulate that. Some things must be part of the solution. Then for illustration reasons, some green shops are selected. They are just showing that per shop we have an information of what its catchment area is. So what is the part of the country from which people are actually going to that shop to buy their contract or their equipment. So what we want to do is we want to choose as few shops as possible, but cover as much of the area of Germany as possible with their catchment areas. And on the right-hand side, you can see an example for optimally choosing 200 shops and covering as much of Germany as possible. In the middle, you can see a graph, the number of shops that you actually open versus the increase in the coverage of the area of Germany. And you see it has a pretty sharp turn-off point where by opening more shops, you cover comparatively little additional area. And so you can see that somewhere between 200 and 400 shops, it stops making sense insisting on opening more to cover more area. So that's giving you the kind of information where you can decide how many shops to reopen, and the actual solution will also give you the information which shops you should choose. So here is how to cast that as an integer linear program, and I'm just going to sketch that. So we have actually described this as a classical problem again, the so-called max K coverage problem, where from a given set, you can actually choose certain subset, and you want to choose as few subsets as possible, but want them to make to cover as much of the total set as possible. Now, because Germany, unfortunately, is continuous, or rather its area, we had to discretize it, and that's something you can see in the upper right. So we've discretized the area of Germany with a regular grid, and now the task is to cover as many of those grid points with the catchment areas of the shop by opening as few of them as possible. And then again, this is a maximization problem, counting the number of those points that are part of the solution, and you can cover a point if you choose a shop that is actually selecting, whose catchment area is actually selecting this point. And then you can restrict the number of shops that you're allowed to open. So this max K coverage problem is, again, and that's perhaps also one reason for the title of talk, an NP-hard problem. So all the problems we have in the background tend to be NP-hard. The nice thing is that it has a natural formulation as an integer linear program, and then we can use that and hence Gurobi to solve it. And also it's approximation hard. And the nice thing is that there is also a natural relationship between the approximability of this problem and the natural ILP, so that there's a relationship between the best approximation factor that you can get and the integrity gap of the ILP. So most of the problems that many of the problems that we're dealing with are actually problems on graphs. Because that's the case, we actually started to implement an API that should make it very simple to set up integer linear programs for solving graph problems very quickly. So we've called it Graph ILP API, and again, it's written in Python, making use of the Gurobi Python API. We are looking at covering at least the following set of topics that you can see on the slide. So things like clustering problems, cuts and flow problems, covering and packing problems, matching problems, factors, and so on. The things marked in green are already implemented. And we are actually looking at open sourcing that. So if this is something you're interested in, I would be happy to hear from you. Good. So, but let's move out of the abstract and look at what we call the Hello World example for our Graph ILP API, which is the map coloring problem. So here on the left-hand side, what you can see is a map of the communities in Germany. And we're actually, what we want to try is color that map with as few colors as possible, such that adjacent communities have different colors. And we can, of course, translate that into a graph problem seen on the right-hand side. So there is a vertex for every community in Germany, and two such vertices are connected by an edge if their areas are adjacent. Now, the problem on the graph is to actually color all the vertices of the graph with as few colors as possible, such that if there's an edge between two vertices, then they need to have different colors. So here is how this looks like in the Graph ILP API. So on the left-hand side, first of all, there is some of the imports that we need. So we need something to actually understand the graph, and we need to have the actually method called min-vertex coloring, which is going to translate the graph instance into an optimization problem. So on the right-hand side, you see the whole program more or less of solving the problem. So first of all, we are supporting some formats of graph and have importers to translate them into internal graph formats. In this example, we get our graph from the so-called networks library, one of the most commonly used graph libraries in Python. So you start with the usual networks graph, you throw it into our import function, and then you throw that wrapped graph into the min-vertex coloring method, and it's going to return you a model, which is of the type of a Gurobi model class. And then you can do whatever you can do with any other Gurobi model here. So if you wanted, you could, for example, add more constraints, you can get information about it, but you can, and that's the most important bit, run the model's optimize function, which is going to invoke the Gurobi Optimizer. And then there is a convenience function that you see on the lower part of the slide, which is going to help you translate the values of the variables representing vertices and edges into an actual solution. So a mapping from nodes to colors here. And if you put that back into the map, you get what you see in the background on the right-hand side. And if you look at it hard and start counting the colors, you will actually find out it's got 6 colors. And then if you've heard about the famous map coloring theorem, you should be skeptical about that solution, because the map coloring theorem tells you any planar map can be colored with 4 colors, and we need 6. So if you believe as a data scientist in your code, the next thing that you do is look back into your data. And we've done that, and we do this by invoking another module from the Graph ILP API, finding a maximum click in the graph. So a maximally totally connected subgraph. And this is one of the obstacles of a graph being planar. So once you have a click of size larger than 4, your graph cannot be planar anymore. And if you run this in exactly the same way as you've done the vertex coloring on the previous slide, then you can again get a Gurobi model representing the ILP for finding such a maximal click, and it's going to return to you what you can see on the right-hand side, a click of size 6. And then, yes, it's clear why you can't color Germany with less than 6 colors. So we are now campaigning to throw out these regions out of Germany to make it 4 colorable. So we've looked at, again, 3 use cases from 2 application areas. We've looked at how to find optimal fiber networks in the sense of optimal return on invest, minimal building cost, and maximal revenue from potential customers. And we've looked at optimal shop footprints. On the one hand, more generally, being able to find optimal countrywide footprints under certain conditions. And the interesting thing about it is that it's a nice combination of integer linear programming and machine learning. And on the other hand, in this application area, we had the question of how to open or reopen shops after the COVID lockdown. And then finally, there is the Graph ILP API for conveniently setting up integer linear programs from graph problems and graph instances. And again, we are about to open source that. And if you're interested in that, or even interested in working on it, just let me know. We are happy for everybody who would collaborate on that.
Thanks again, and we'll see you in our next webinar. All right, take care. Bye-bye.